right, so we talked about the different kind of forces, and we talked about, there's one that I talked about and I said I'm going to come back to it later, which is the friction force. So there are two kinds of friction force, as we said, and they are the sliding versus static friction. Okay, what is the difference? Just really briefly, when we talk about sliding friction, it's the result of like when something is moving, sliding, and it gets in contact with the other surface, that's slowing it down for whatever reason it's slowing it down. We call this the friction force. So the friction force results when an object slides across a surface. Okay, and like if we talk about a car sliding across the road, you know, that there will be a friction force created between the wheel and the road. You know, that is the friction force. Now, the formula for the force friction that is a sliding friction is the coefficient. So it's like one side big M, the other one is short. That's friction sliding times the normal force. So I'm going to say that so this is your coefficient of sliding friction. So every surface has a coefficient to it. All right. It's usually a constant and it depends on the nature of the surface that this object is in contact with. So that is the sliding friction. Oops, I don't like when it smears like that, but it's okay. So that is the sliding, all right, friction. Now, what about the static? What about if we talk about static friction? What is a static friction? Okay, it results when the surface of two objects are at rest to one another, and then a force exerts in one of the objects to set the other object into a kind of relative motion. It's like the balloon when you rub the balloon into your clothes and you just put it, you know, on the wall and it's gonna hang up to the wall. There is a force. Well, it's an attraction force, but there was a force between that balloon, the static force between that balloon and the surface of the wall. So this is basically what the static friction is. And let's just write this down. It results when the surface of two objects are at rest relative to one another and a force exists on one of the objects to set it into motion relative to the other object. Right? And there is, you're really not going to see a lot of friction, static friction examples, but I would like to just introduce it to you and tell you that the friction, the force of friction, the static friction formula is usually less than or equal to the coefficient of the static friction times F normal. So it's the same formula, but for this one, the friction usually is less than. Okay? So in all these cases that we've been talking about, we notice that this force is actually causing my object to actually move. All right? So when we talk about an object that is actually moving and it's not stable or standing there anymore, that means we are talking about Newton's second law of motion. So all the ones we've been talking about since we started the balance unbalanced force, you're going to keep this in mind and don't forget it, that we are talking about Newton's second law of motion. All right. So now since let's write. Now since we've been talking about Newton's second law of motion and we are referring to different forces and we are referring to different directions, which means we need some sort of diagram so that we can find what is the net force that is acting upon these, objects or whatever. All right. So how do we draw these diagrams? So this is an extremely important unit, okay? And I want you to focus on this step by step, and you're going to use a lot of CERs. So the title is Drawing Free Body Diagrams. Okay? So or we can say it's forces and its representations. That's in Newton's second law. All right? So free body diagrams are used to show the magnitude. So they are used to show the relative magnitude and direction of all forces acting upon an object in a given situation. So I know we've done a little bit of this earlier. And let's say I have, a box. And we for sure know that we have that gravity force. And then there is another equal force that is going upwards. And we have the applied force that is going to the right, and we have a friction force. I'm just showing you the diagram. There's really nothing. It's just, I just want you to see what it means when we talk about diagrams or free body diagrams, all right? All right, so let's see. Let's do a few examples, and we're going to apply the method that is, just let's see how the free body diagram will be applied to this. So let's do example 1. A book is at rest just give me a minute, you guys. All right, a book is at rest on a tabletop. Okay, so how do we draw this? Okay, how do we do the free body diagram for this? So I have the book and it says it's at rest. That means it is not moving. So that is the book, all right? And it's at rest. That means what do we have? We have the force pulling downwards, gravity force, and then we have the normal normal force, and then we know that this is the net, the summation of force, which is the normal plus the gravity, which is gonna cancel each other. So the net force would be 0 Newton, which means it's at rest, and this would be your free body diagram. All right, so let's work on example number 2. All right, so let me see if I can find that example here so that instead of me, writing it down, I can just cut it. I think it should be here. Yep, I actually do have it. I'm just gonna glue it and we will go over it. All right. So I'm just going to start. I know it's so weird the way I cut it, but who is judging right now? All right. That's example number 2. And what do we have here? We have a gymnast holding onto a bar, is suspended, motionless in mid-air. All right. The bar is supported by 2 ropes that attach to the ceiling. Diagram the forces acting on the combination of gymnast and bar. A free body diagram for the situation will look like this. All right, so what do I have? I have that girl. That is the girl or the gymnast. I don't know why I thought it's a girl, but that is the gymnast. She's holding onto a bar. All right, so when she's holding onto a bar, you should right away know that there is this force that is pulling downwards, which is the gravity force. And then there's another upward force. One of them is the tension force. Okay, that is acting upon the girl. And the other one, that's the tension force for the girl and the rope. Because remember, she's hanging on into the rope. And then here comes another force that is acting as the normal force. So there is the tension force, and there is the normal force that is going to cross out with the gravity, and then the force that is going to be left is that tension force that is in between the gymnast and the rope. Okay? All right, let's do example 3. What do we have for example 3? We have an egg that is free falling from a nest in a tree. So we have an egg falling. Can you now imagine the forces without me doing it from a nest in a tree? Okay, neglect air resistance because you know that there will be air resistance, right? Okay, neglect that air resistance. What is the body, the free, oops, I'm sorry. What is the free body diagram is going to look like? So we got, this is the bird, and the bird just fell down, and that is the gravity force. I keep writing the whole thing. It should only actually be the FGRAV, but I just want you to get used to them. All right, now let's have another example, and that would be example 4. All right, let's talk about a flying squirrel that is gliding, right? A flying squirrel from a tree to the ground at a constant velocity. So, flying squirrel. So that's a constant velocity. Then I know I'm talking about Newton's first law of motion, right? Flying squirrel is gliding at a constant velocity. So when we talk about this, we know that we're dealing with Newton's first law of motion. So I got gravity and we know that we have the air resistance that is upwards. All right, so let's do example number 5, and I'm just going to cut it because I don't want to really write it down. I messed up the, oh, all right, it's okay. So let's do example number 5. So what do we have? I know the top is cut. I'm just going to write down the word that I cut by accident. So we got a right word force that is applied to a book in order to move it across the desk with a rightward acceleration. I'm talking about acceleration and force. That means I am talking about Newton's second law of motion. All right. Consider frictional forces. So there is the force between the book and the desk. Neglect air resistance. So F air is 0. We got a frictional force. We have an acceleration. So that's what we're going to draw. We're going to draw the book. And we have the gravity, the force of gravity going downwards. Hello. Yeah, I will. Do you want me to meet you there, or how are you guys doing it? Okay, I'm coming. All right, bye. All right, so it's the gravity force downwards, the normal force upwards, and then I have the applied force to the side and the friction force to the other side. All right, we're gonna do more examples, but for now I'm just gonna